Okay, so today I'm going to talk to you guys about motion graphs, and this is the slower version, so if you're maybe a little less sure of yourself, you can go ahead and watch this version. I apologize, it's a little bit longer, but that's okay. So my question for you is this: are those two graphs the same? The answer is that you can't really tell, because a bunch of critical pieces of information are not there, and so we need to try to investigate a little bit more and get better information. So let's imagine now we put what's actually being graphed on there. So knowing that they're motion graphs is not enough. We, on the left, have the position versus time, and on the right have a velocity versus time. And they're very different graphs if one is position versus time and one is velocity versus time. You can actually split up those graphs into three different sections based on what you see. And each of the three sections has kind of a different motion that it's describing. So for the position versus time, the object is clearly moving away from the reference point for the first third. For the second third, it's moving back towards the reference point. And then for the third third, it is actually moving back away from the reference point one more time. Now, how does that compare with the velocity versus time graph that you see on the right? Again, it can be split up into thirds. That's no problem. Just for the same reason that the other could. But if we're talking about velocities, you can see in the first third that the velocity is going up, and so therefore the object is speeding up. Notice though that it's moving away from, it still has a positive velocity, so it's moving away from the reference point. It's still moving away from the reference point in the second third, it just is slowing down. So it still has a positive velocity, it's just changing in the downward direction, so it's slowing down. The final third, it speeds back up again. But again, it's still moving away from the reference point. And so you can see, just based off of those thirds for each of the graphs, that they're not the same. Another thing I could do is I could change the units that are represented in each of those and make them both position versus time. So on the left-hand side, I have meters versus seconds, so that's a common one you'd see in this class. And then on the right-hand side, we have light years versus years. So that might be an example of a situation in which you were talking about galactic motions, things like that. So obviously, we're talking about very different things there. Finally, you can look at the shapes. And the shapes of the graphs will tell you what the nature of the relationship is between the two variables. Even if the two variables are the same, like x versus t, if they have a different shape, they're going to have a different relationship. On the left-hand side, we have a linear relationship, and so it conforms to the y equals mx plus b format for a line, and we would call that a constant motion because the slope is constant as it goes across, as it moves across the floor or wherever it's moving. On the other hand, on the right, we have a curved relationship, and so we could call it exponential or polynomial if we wanted to. And that exponential or polynomial relationship is one in which the motion is changing. As you can see, it gains more position as the time goes on per unit of time. And so as a result, we could say it's speeding up just based on the fact that it's curved like that. So when you're analyzing scatter plots, for example on a ACT test, you want to do three things before you do anything else. First, you want to go ahead and identify what is actually on the axes. What is actually being represented there. Second, you want to get a sense for the size by looking at the units. And third, you want to look at the shape, and the shape is going to tell you what sort of relationship exists between the two variables. Oftentimes in this class we'll have exponential, polynomial, or linear, and really that's it. Occasionally we'll have no relationship, so that would be a horizontal line. On the left-hand side, the graph of that motion shows something similar to what you might see in Unit 1, the unit we just finished. And then on the right-hand side, that's accelerated motion with the curve in it. And so that is really what we're studying in this unit, Unit 2. Okay, so now how can I take the position versus time graph on the left and make it into a velocity versus time graph on the right? Well, if you remember, in a linear relationship, actually in any relationship, the slope of the line on a position versus time graph is going to tell you the velocity that the object has at any particular time. It just so happens that if the relationship is a line between x and t, then the slope doesn't change. And so we would say that the velocity is constant. We saw that in a number of our labs that we did in the class. So to have a constant velocity, you would have a horizontal line. In other words, there's no relationship between the velocity and the time. What I mean by that is the velocity stays constant no matter what time you're looking at it, and so there's no relationship. So that would be what we studied in Unit 1. It does occasionally happen that we'll come up against these again, but for the most part, we're going to stick with the curved relationships where we have some acceleration, because really our goal is to try to figure out what causes accelerations and then how to predict how much acceleration there will be. So going back to the curved graph that we saw before, you see there's an exponential or polynomial formula for it. Well, it turns out that if you look at that master motion equation, the delta x equals v1 times t plus 1/2 at squared, you really are looking at the exact same formula for a curved line in this space. Now, just keeping the math out of it, you can see just off the top of your head there that the slope of the curved line is increasing. And so as a result, you know for a fact that the velocity must be increasing. And if it's increasing in a regular way, then you can say that the velocity has a linear relationship with time. Now let's imagine that you want to take a velocity versus time graph and you want to use it to be able to determine what the acceleration is that an object is undergoing or experiencing. Well, let's go back to our slope analysis. So slope is rise over run, which is the change in the velocity over the change in the time. But look at what we also know is the change in velocity over change in time. It's the acceleration. So in this case, velocity versus time, we use the slope analysis to determine the acceleration. If you remember back when we had position versus time, we used the slope analysis to determine what the velocity was. Now, how could I use a velocity versus time graph to determine the displacement? Well, there's an interesting trick, and it involves calculating the area under a curve. And so I'm going to show you here that the area under a curve is actually equivalent to the amount of displacement, mathematically speaking. And so on the left-hand side, or sorry, the right-hand side, I'm going to show you that the average velocity that an object has is equal to its initial velocity plus its final velocity divided by 2, because it's an average, and you can do that. So I'm going to go ahead and solve the average velocity formula for displacement. That's delta x there. And I'm going to get delta x equals v_av times t. But we know from the formula above that v_av is also 1/2 delta v, 1/2 times the change in the velocity. So I end up with this displacement equals 1/2 change in velocity times time formula, which is kind of weird. It's not something that we have, and I'm only using it here in this one case. It's not on your formula sheet or anything. But if you look on the left, you can make that shape into a triangle. And you might remember that the area of a triangle is 1/2 base times height. And the base, in this case, is the time, and the height, in this case, is how much the velocity changes. And so as a result, the area is equal to 1/2 times the change in the velocity times the change in the time. And you may notice, if you look to the right-hand side, that that's exactly the same thing as the displacement formula. And as a result, the area under a velocity versus time graph is the displacement. And so it's a kind of an easy trick. Now, for those of you in calculus, this should be very familiar, or will be very familiar to you, because calculus AB is really about slope analysis and area analysis. We can do it with algebra 2, so we can just kind of get around that. That's okay. Last but not least, we want to talk about what kind of accelerations we're going to explore in this class. And so we really are only looking at 2 kinds. And they're kind of the same kind, but I just want you to see what they look like graph-wise. So the first one was what we did in Unit 1, and that is when there's no acceleration. So the motion is constant. It's moving, it's just not accelerating, it's not changing its motion. On the right-hand side, we have an acceleration graph where there is some constant acceleration. So in other words, it's getting faster, in this case, could be getting slower, which would be a negative acceleration, but it would be constant either way. And so we are not going to deal with accelerations that are changing very much in this class because it gets to be kind of tricky, and you really want to have calculus tools to be able to handle that. So that's all for here. If you have any questions, please go ahead and let me know. Hey, thanks for watching.